Hello everyone. Today we are going to discuss the problem Planet Queries 1 from CSES Graph problem set. Let's go through the problem. You are playing a game consisting of n planets. Each planet has a teleporter to another planet or the planet itself. Your task is to process Q queries of the form when you begin on planet X and travel through K teleporters, which planet will you reach? The input has two integers n and q, the number of planets and queries. The planets are numbered 1 to n. The second line has n integers t1 to tn. For each planet, the destination of the teleporter is given to you. And it is possible that ti is equals to I. That is, it is possible that the planet is getting teleported at itself. Finally, there are q lines describing the queries and each line has two integers x and k. You start on planet X and travel through k teleporters. So you have to output what will be your final planet B. So you need to print the answer to every query. And if you look up to the constraints, the value of number of planets and queries can go up till 2 into 10 power 5. Planets are numbered 1 to n. K, that is the number of times you're teleporting, can go up till 10 power 9 as well. Okay, cool. So how we can actually solve this? Let's first of all try to understand what the problem is. So I have just drawn the sample input over here. So if you just notice, we have a graph in which there are 4 planets, planets 1, 2, 3 and 4. Planet 1 is getting teleported to planet 2, 2 is getting teleported to 1, 3 is getting teleported to 1 and 4 is getting teleported to itself. Then you have this following queries where the first input in the query is actually the planet number and the second input is how many times you are getting teleported. So let's try to answer these queries. So if you just notice, first is planet 1 and it is getting teleported 2 times, right? So after one time teleporting, planet 1 will reach planet 2 and the second time it will reach planet 1. So the answer to the first query will be planet 1. Similarly, for the second query, planet 3 is getting teleported 4 times. So let's see where will it be reach. First time we will reach to 1. Second time we will reach to 2. Third time we will again reach to 1. And fourth time we will again reach to 2. So you can just notice that if we teleport planet 3 4 times, we will reach planet 2. Similarly, for planet 4, we are teleporting 1 time and since it is getting teleported to itself, the answer to this particular query will be 4. So I hope the problem is understood to every one of you. If not, just go through the problem once again and you will be able to understand that. Okay, now how we can actually solve this? We are given that number of planets can go up till 2 into 1e5, right? And number of queries can also go up till 2 into 1e5. And the value of k, that is number of times you are teleporting, can go up till 1e9. So if you are thinking that you will brute force it, like for every query, for every planet, you will just try to go like to every jumps. Like let's suppose for planet 3, the value of k was 4. So first of all, from 3 you started. You first of all went to 1, then you went to 2, then again you went to 1, and then you again went to 2, and you teleported 4 times, you output 2. If you are thinking you are going to do that, then that won't work, right? Because again, the number of queries is also very big and even the value of k is up till 1e9. So it does not work, right? So how we can actually solve this? So one important thing that to notice in this particular graph is there is one speciality in this graph. What is that? Can you guys tell me? The speciality is that from a node, you have only one outgoing edge, right? From a node, you have only one outgoing edge. That is, if you start at a node, there is only one edge that you can take to move to other node, right? Okay. And this problem involves something like k jumps. Like you are from a planet, you are making k teleporting, you are teleporting k times, and you're reaching to a particular planet, right? And we have understood by looking at the constraints that, okay, if we are thinking that we will brute force it and go to every k planets in the path and then output the final answer, then that is not going to work. So to solve this problem, where we need to find somewhat of kth parent, like when we talk of trees, this comes into our mind, kth parent or something like this, kth ancestor of a particular node. But over here, if you just look, we want to find a kth planet at which we will be. Like basically after k jumps, the planet that we will be at, I am just naming it as kth planet. So you want that kth planet, but you don't want to brute force it, like to travel over every planet after k jumps. You don't want that, right? You want the shorter answer. You want to do it in an optimized manner. So how we can actually do this? So to solve these kind of problems, we have a very, very common concept called as binary lifting. So I'm going to give you some context of what actually binary lifting is, because this problem is only about this concept. So I'm going to give you some context, but even if you don't understand after this, I am very free to make a complete video on binary lifting as well. Okay. So what is actually binary lifting? I am just going to discuss what we actually do in binary lifting for this particular problem. Okay. So what we do is, for every node, we pre-compute 2 power jth parent. Over here I am naming it as parent because this is a very general concept, but for this particular problem we just want the 2 power jth planet, right? Basically, if you understand that 2 power j, we will discuss it what 2 power jth means. Let me just write this statement. For every node we pre-compute 2 power jth parent for that node. Now what does this mean by computing 2 power jth parent? I will just take an example over here. Let's suppose for node 1. Okay. Can you guys tell me for node 1, what will be 2 power 0th parent? What do we mean by 2 power 0? 2 power 0 is 1. 1 means the first parent for node 1. The first parent of node 1 is where if we are teleporting only one time, which planet at we will be. So 2, right? So I'm just writing 2. Similarly, what will be the 2 power 1th parent of node 1? 2 power 1th parent means we are teleporting 1 2 times, right? So again, if you look, from 1 we move to 2, then from 2 we need move to 1. So for 1, 2 power 1th parent, that is the second parent, is actually 1. Okay. Now similarly, 2 power 2th parent. 2 power 2th parent means fourth parent for node 1. Basically, if we are teleporting 1 4 times, then which planet we will be at? So if you just look from 1, first is 2, second is 1, third is 2, fourth is again 1. So 2 power 2th parent of 1 is again 1. And like this, you can simply continue. So what I am saying is, for each and every node, we will pre-compute 2 power jth parent. Now this value of j will go up to what? That we will discuss. That is very intuitive as well. You guys will be able to figure it out by yourself only. Like up till which value we will compute, like 2 power 3, 2 power 4, up till which this power we will compute the values. We will discuss that, but it is very intuitive. But just now understand this thing, that we are going to pre-compute 2 power jth parent for each and every planet. Now again, if you are thinking that we are going to traverse over the nodes and pre-compute that, no, we are not going to do that. There is a simpler way to do that. But for now, just assume we already have the 2 power jth parent for each and every node. Now how does it help us? I will discuss how we will have this 2 power jth parent, but before that I want to discuss how is this going to help us. So for that, I am just going to draw a simple graph, which is just looking in the form of tree for now. Let's suppose we have graph this. This is the graph we have. Tree is also a graph, right? Okay. Let's suppose I tell me what is the third parent of node 10. If I ask you this thing, what is the third parent of node 10? This is the node 10 that I have, right? What is the third parent? The first parent is 7, second parent is 2, and third parent is 1. So the answer to this particular query will be 1. But how we are actually going to compute this? Okay. First tell me what we will store. For 10, can I say 2 power 0th parent, 2 power 1th parent, and 2 power 2th parent? Can you name these parents for me for node 1? 2 power 0th parent is 7, that is the first parent. 2 power 1th parent is 2, that is the second parent. And 2 power 2th parent is, it does not exist, so let me store minus 1. 2 power 2 means fourth parent. Fourth parent does not exist, right? So I'm just storing minus 1. Similarly, for node 7, can you say me again all these three values? For now, only these three values are needed for this particular example. That's why I'm just keeping it up till 2 power 2. Okay. 2 power 0th parent for 7 is 2. 2 power 1th parent is 1. And 2 power 2th parent does not exist. So I'm just storing it as minus 1. And similarly for node 2, can you say me 2 power 0th parent? It is 1, right? 2 power 1th parent does not exist. 2 power 2th parent does not exist. Okay. These are the values I have. I have populated it for each and every node, but for this particular example, for this particular node 10, I only need these values. So I have just written these three values. Okay. Now we want a third parent of node 10, right? Can you guys tell me, or can you guys think that what is the binary representation of 3? How does binary representation of 3 looks like? Binary representation of 3 looks like this, right? 1, 1. 0, 1, 1 if I am storing 3 digits. It looks something like this, right? This position is actually 2 power 0 position. This is 2 power 1. This is 2 power 2. So when I am talking of third parent for a particular node, what I am actually talking is, let's suppose I have a node X. Okay. I have a node X and I want a third parent. So what I will do is, I can just traverse either from left to right or right to left. Let's suppose I am traveling from left to right. Or sorry, from right to left. Okay, let's suppose I am traveling like this. So whenever I get a set bit, like over here in the 0th position, I got a set bit, right? So I can just convert my X. To 2 power 0th parent of X. Okay, and this is done. Now I move to the other bit. The other bit is also 1. So whatever node I got over here, I will just convert it to, let's suppose this node that I got was Y. So the next node will be 2 power, since this bit is a set bit, so it will be 2 power 1th parent of Y. So basically what I mean is, the third parent for node X is actually 2 power 1th parent of 2 power 0th parent of X. Let us understand this with the help of this example. I want a third parent of 10, right? So can you guys tell me what is the first parent of 10? Can you guys tell me what is the first parent of 10? The first parent of 10 is 7, right? So over here, the value of Y that I will get, will be 7. Now I move to this other bit, and since this bit is also set and this position is 2 power 1th position. So now I will look to 2 power 1th parent of this particular node 7, and I can clearly see from the table that 2 power 1th parent of node 7 is 1. So now when I perform this 2 power 1th parent of Y, I will get the node as 1. And since no other bits are set in the binary representation of 3, I have already got the third parent of node X, that is 1. So now I think you guys would agree that if I have 2 power jth parent for each and every node stored, I can easily find the kth parent for that node in just what time? In just big O of logarithmic value of k time. And k can since maximum go up till 1e9 for this particular case. So definitely in just 30 operations, I can, in max 30 operations, I can just find out what is the kth parent for that particular node. So I hope that this thing is clear to each and every one of you. But now the only thing that is left is how actually we are going to store 2 power jth parent. For storing 2 power jth parent, can you guys tell me which is the easiest one to store? Which is the easiest one? I think you all guessed it right. The easiest one to store is 2 power 0th parent. So if I already know 2 power 0th parent for each and every node from the input given to me, right? This input is already given to me. So I already know 2 power 0th parent of 1 is 2. I already know 2 power 0th parent of 2 is 1. I already know 2 power 0th parent of 3 is 1. I already know 2 power 0th parent of 4 is 4 itself. I already know 2 power 0th value from the input. So let's try to use this. I already know 2 power 0th parent, right? By using this 2 power 0th parent, can I get 2 power first parent of every node? Can I get this? Just think. Let's suppose I have node X and I want to reach 2 power first parent of X. Okay. Can I say 2 power first parent of X is nothing but 2 power 0th parent of 2 power 0th parent of X? Can I say this? Just think. This is actually nothing but 2 power 0th parent of X. And this is also nothing but, if this node is Y, then this is nothing but 2 power 0th parent of Y. Can I say this? If you just look from the example as well, if I want 2 power 1th parent, basically second parent for node 10, it is nothing but 2 power 0th parent of 2 power 0th parent of 10. 2 power 0th parent of 10 is 7 and 2 power 0th parent of 7 is 2, and 2 is nothing but the 2 power 1th parent of 10. Similarly, if I want 2 power 2th parent for a particular node, if I want 2 power second parent, that is basically 2 power 2th parent, 2 power 2th parent for a node. So can I say that if the node is X and if I want a 2 power 2th parent, then it is nothing but 2 power first parent of 2 power first parent of X. This is 2 power first parent of X. And let's suppose if this node is Y, then this final value is nothing but 2 power first parent of Y. And if you just look, if we just compute in order, we already have this 2 power 0th value. So with help of this, we will be able to populate 2 power 1th value for each and every node. Then with the help of 2 power 1, we will be able to populate all 2 power 2. With the help of 2 power 2, we will be able to populate all 2 power 3. And this is how we can actually pre-compute 2 power jth parent for each and every node. And this is how actually binary lifting works. This problem is actually the exact implementation of binary lifting. We are actually computing 2 power jth parent and finding the kth parent for a particular node. This concept is very, very important even while problems of least common ancestor, and definitely we will look at when we make solutions for trees as well. But for now, just understand what is binary lifting, how do we pre-compute 2 power jth parent, and how do we actually use that 2 power jth parent values to compute the kth parent of any node in just big O of log k time. I hope the solution is clear to each and every one of you. Let's go through the code and you will be able to understand it better. Okay, one more point. Till which value we will compute this 2 power jth parent? Till which value? Just think. Just try to put some pressure on your brain and think, till which value do we actually need? We need up till maximum of log k value, right? We want up till 10 power 9 parent. So we will compute till 30 and that will be good to go. Like we won't need more than that, right? Okay, let's go through the code. So I'm computing till 29 only in the code because 2 power 30 is greater than 1e9. So I'm not just taking that, okay? So I've just computed a global array, parent array, where the number of nodes can go up till 10 power 2 into 10 power 5 and parent I am storing till 30, 0 to 29 basically. Taking nodes and queries as input, taking the input of the 0th parent for a particular node. Okay, the input is given that the particular node is getting teleported to which node. So that teleported node becomes actually the 2 power 0th parent for that particular node I, right? So I'm storing that, and since I am storing the values in zero based indexing, I'm also subtracting it by 1. Now over here I am just populating all the 2 power jth parent from j equals to 1 till 29. So just j equals to 1 to 29 loop, going over all the node, and 2 power jth parent of that node is nothing but 2 power j minus 1th parent of 2 power j minus 1th parent of node I. This is how we are getting 2 power jth parent of I. We have already discussed this. So this pre-computation happens if you just look in just big O of 30n, basically big O of n log k time, right? This is just a lambda function. Let's ignore this for now. Going over all the queries, taking the inputs of node and the number of times it is getting teleported, converting the node to zero based indexing and printing the kth parent of this node. And since the answer wants us to print the value in 1 based indexing, also adding an extra 1. Let's see the code for kth parent. This is just a lambda function I wrote so that I don't need to pass these parent values and all. So node and k I am taking as input and the return type is int. So I am going over here, I am just going from left to right. You can either go from left to right or right to left in the bits, in the binary representation, okay? Going over all the values from bit position 29 till it is greater than equals to 0. If the bit value is set, then I am transferring my node to its 2 power ith parent, only if the bit is set, okay? And at the end, I am returning the node that I got. So this is how I am computing 2 power kth parent, I am computing the kth parent for this particular node in just log k time. So I hope this solution is clear to each and every one of you. Thank you.